Okay, good morning. Why don't we get started? So we'll continue on today, starting with a demonstration of using C structs, which I tried to do last time, which is the way you create so-called user-defined types in the C programming language. And so, as usual, please make sure you're keeping up with the reading. That's the reading assignment. Make sure you're keeping up, get that read by the 15th. I will be administering written exam number 1. It's either going to be a week from today or a week from Monday. End of this week marks 7 weeks of the semester, and I like to give it at the true midterm or middle of the semester, which is at the 8-week mark. Okay, I will certainly announce details about that if I think I'm going to do it a week from today. But nonetheless, the format of my exam are essay-style questions that are purposed with measuring your understanding of the material. So there are a number of choices one can make in an operating system design. There are a number of subsystems and mechanisms, and those mechanisms work together to give rise to certain behaviors. And so the type of question I would ask you would be a general question about some scenario, and then ask you why, right? And so it's up to you to put together all of the why things, right? They can be more than one why type of answer, right? But knowing what the system bus is, what the implication is of passing data on the system bus. If there's too little data, if there's too much data. What is memory management? What is process management? So basically the material from chapter 1 and chapter 2, okay? And in the written exam, each student is allowed an 8.5 by 11 sheet of paper, so that's a standard sheet of paper, both sides, to write whatever you want on that piece of paper as your notes to bring with you in the exam. So you can bring a so-called cheat sheet with you to the exam. I don't expect you to memorize material. I feel that's a useless exercise, and that's why we have reference material out there. So I fully expect that you'll bring that 8.5 by 11 sheet of paper, write whatever notes you feel are important to you to help you remember things, and you bring it to the exam with you, and you take the exam with them, okay? And so my style, for those of you who've never had me for a class, which is most of you, my style is to, I don't really ask definition questions, right? I ask scenarios, and then it's up to you to bring to bear all of the material and the interactions among components in order to answer the question. Any questions about this? And so what I'll do this evening, around 7:30, I'll send out a message as to whether or not it's a week from today or a week from Monday. It's looking more like it's going to be a week from Monday. Any questions about that? No questions? Okay. So please look out for that. I'll send it both as an email through Blackboard as well as on Slack. So please make sure you're looking out on both of those forums. Okay, so why don't we begin? So I'm going to exit the show here, and we'll bring up the virtual machine where Ubuntu Linux is running. And just as I had suspected last time, when you pause a virtual machine and you're connected to one network, which is what had happened when I was at home, and then you unpause that virtual machine and you're connected to a different network, the virtual machine struggles to reattach. So VirtualBox doesn't do that, but Parallels seems to have an issue with that. And if you're interested in buying Parallels on Mac OS, there's a student discount. You need some proof that you are a student, like a copy of a transcript or a student ID that's current, and then you Google search for Parallels student pricing, and I think it's $39.99 instead of the personal edition, which is $79.99. So if anyone is interested, it's really up to you. VirtualBox works good enough, but maybe you like Parallels. Okay, so let me log in. And we'll proceed, OSC, with the material at hand as it pertains to C structures. Control-Option-Tab, there we go. So we have our command line interface instance. Let me increase the size of this so people in the back can see a little wider. Make it a little taller. Okay. All right, so I log in, I'm in my home directory, me being OSC, which is the default account, the single account that's on the VM instance. So let me take a long listing. I'm gonna go to that directory I created where I've sort of been working on a bunch of stuff for all of the examples. So I'm gonna call my file test structure.c, and in this, it's a fly, in this test structure.c, I'm going to use the usual includes that I think I might need. So I'm going to number sign include standard io.h. So I'm going to pull in all the header file definitions for things like printf, and that should almost be automatic. And then I'm going to write my make file. So int, rather my main routine, not my make file, int main, int arg c, the argument count, char star star, so a pointer to a set of strings, arg v. Okay, so open and close the block, and I'm ready to go. Now main needs a return type of an integer, so right away I'm just going to type return 0 to satisfy main, where return 0 means there were no problems. And just for good measure, I'm going to put a printf main started \n, that's the carriage return. So there's my basic shell of the program, and let's add to that. But because we want to compile and link it, and we're going to compile and link it multiple times, I'm going to modify the make file to compile this test structure.c. So I'm going to edit the make file, and I'm going to add another default rule for the executable, test structure. Right, that's the executable. There's no extension on the executable. I'm going to add a compile to create the object file for this test structure. So test structure.o is the result of compiling. The dependency is test structure.c, and the action to take if the dependency test structure.c is newer than the object file. G is GCC. I'm going to compile, run the GNU compiler collection, test structure.c. Okay, so there's my compile, and I separate out the compile from the link. So I need a link line that's going to paste together the object test structure.o with the system libraries made available by the operating system with the object to create the executable. So I'm going to add another line here. Test structure is going to be my executable name. The dependency is test structure.o, and the action I take is to run the linker GCC, GNU compiler collection, tell it to link. So I use that .o specification to GCC on the command line. Test, the output is test structure, bless you, structure. And then it's going to paste in with the system libraries the object file test structure.o. Okay. Any questions about this? Yeah? No? Okay. So let's try this out. So if I type make, oh, did I misspell it? Test. Oh, yeah, I forgot the C. All right. Strutor, let's see. Structure. There we go. Structure. There we go, misspelled it. There we go. So let's try this out. No, let's see. Okay, at least I'm consistent in spelling it, right? Let's see. I misspelled it there. There we are. Okay, so let's run the executable. Test structure. Okay, main has started. Okay, good. So let's go back to the C program. So we have the basic plumbing in place to compile and link the C file. And we have that very basic stub of a C file. So let's look at test structure. Okay, so when you look at any kind of C program, you see a number of types, like int. Int says it's an integer, so that means it's signed. and it's 32-bit is the size of an integer. You can have a long integer, which is 64 bits, which is the full word size, if you will, for 64-bit architecture. You also have other types like char, right? You have float, you have bool, all sorts of types. But sometimes you want to create a type that is custom, right? You want to have a type which is an aggregation or a set, as it were, of all sorts of pieces of information. Let's take a typical example like a linked list, right? You want a list of records. Maybe it's a banking application or some student application or what have you, and you want to be able to search for records, and these records carry with them a bunch of pieces of information. This is where a so-called user-defined type comes in place. Now, in an object-oriented language like Java, a class is a user-defined type. And that user-defined type acts just like any other type in the language. It's so-called first-class citizen, as they say in the literature, first-class citizen of the language. And so you define this user-defined type, and you give it a name, and then you can now use that name to declare variables, and that variable will be carved out of memory somewhere, and that region of memory where that variable is carved out is going to have a format as described by that user-defined type, right? And so the example I'm going to carry through is going to have 2 character arrays, and it's going to have a floating point number to represent, say, a bank account, the first name, last name, and the balance, for example. And then what we'll do is we'll dynamically allocate that using Malloc, and then we'll loop through, input some values, and then print out what was saved, and then free that memory. Okay, so in C structures, you type the word struct, right? The name, record struct, right? And then open close curly brace and semicolon to end that statement. So inside of the structure, you can specify a number of types. And let's say, for example, we're going to have 2 character arrays, and they're going to be of some maximum length. So as is my own practice, and you don't have to do it this way, you can use variables, you can hard code numbers, but it's good practice to keep things that could change with your program in one place, so that if you wanted to change the size of things, you try to change it someplace in a header or up at the top of a file, and everything else adjusts accordingly. So I'm going to number sign define name length, and I'm going to say all string names are 1024 characters in size. Okay, so now I'm going to introduce a character array inside the structure, and I'm going to call it char first name, and its size is going to be of size name length. Okay, so this says I have this type, and it's called record struct. And this record struct, this keyword here, keyword modifier structs, tells the compiler, the C compiler, that this thing is a user-defined type. And this is its name. And in between the open and closed curly brace are the definitions of all of the types or pieces of data structure, if you will, data structures, if you will, that are associated with this name I'm calling rec struct. Okay? All right. Any questions about this? No? All right. So let's also define another character array, and let's call that last name, and it's going to be of size name len. Okay, and then finally let's define a floating point number, so it has a decimal point, and let's call that balance. Okay, oops, yes. All right, so here we have a type, and struct tells the compiler it's a user-defined type. The name, like how you'd have a name called int or float or char, here is a type, but its name is called rec struct. The keyword modifier struct tells the compiler that what follows is a custom name, and this custom name is going to be a type alongside how you have an integer type, a Boolean type, a float type, etc. And this type happens to be a layout that consists of a character array accessed by variable first name, and it is of length 1024 characters, and it's going to be followed by another character array accessed by variable name last name, and it's going to be 1024 characters followed by a floating point number accessed by name balance. Okay, so we have three pieces of information collectively, and they kind of look like instance variables if you're used to something like Java or any other object-oriented programming language. But in this case, C's mechanism allows you to extend the type system, if you will, with something that you name in a custom way. Okay. Any questions about this? Make sense? Yeah. Okay. So I'm gonna do a bunch of other includes just for some bookkeeping. Number sign include string.h, number sign include standard library.h, and number sign include standard def.h. Now, these have different pieces of information, like string allows you to take the string length of things. Standard library allows you to do things like malloc, and standard def includes other definitions like null in all caps and things like that. Okay, so let's begin. So I'm going to create a pointer here, and this pointer I'm going to put it as is my style. You can season to taste. I'm going to have a pointer, and that pointer is going to reference one of these record structures. So I'm going to say struct rec struct star, right? So pointer, and I'm going to call it the records, right? And I'm going to initialize it to null. Okay. So what this first line does, this local variable, it says there's a variable called the records, right? And the records is going to be a pointer. It's going to contain a memory address. And the memory address it's going to contain is going to be the location of one of these rec-struct user-defined types. And this rec-struct user-defined type is laid out as specified up above. Okay? All right. So when I declare this pointer, that pointer can then be the starting place for a list of such rec-struct user-defined types. So let's go ahead and let's allocate some number of them. So let's assume, for the sake of argument, it doesn't have to be 3, but 3 is a nice small number. I'm going to define a list of 3 of these rec-struct structures. And I'm going to put them in a list, and that list is going to be referenced by this pointer that I'm calling the records. So number sign define num records recs as 3. Okay. So now I'm going to use dynamic memory allocation. I'm going to use malloc. And if you're going to allocate memory, you also are responsible for deallocating that memory when you're done with it. So I'm going to say the records. It's going to be assigned to, so I'm going to fill in the records pointer variable with a memory address. And that memory address is going to be returned to me as the result of doing memory allocation or malloc. So I'm going to do it partially and then explain one point and fill in the rest of this. So malloc, memory alloc, and what malloc says is if you give me a parameter, that parameter must represent the number of bytes that I'm going to allocate. Now, we have a little bit of a problem here. Well, I want to allocate some number of rec-structs, but I need to also count how many bytes this rec-struct data structure takes, because I want to allocate 3 of them, right? So 3 many of these rec-structs, however big a single rec-struct is. Now, knowing how big the types are, a float in IEEE 64-bit floating point representation, because this VM is a 64-bit machine. 64 bits, that's 8 bytes. And then we have a character is 1 byte, and we have 1024 of them. So that's 8 bytes for the float. That's 1024, that's 2048. 2048 plus 8 is 2056. Now that's a little bit tedious, right? Who wants to go and do that for all of your structs? So there's a routine made available called sizeof. And what sizeof does is if you give it a type, like integer, float, or even a user-defined type, sizeof will actually measure the number of bytes that thing occupies, and it'll do the work for you. So when I call malloc, instead of giving it the actual byte count by calculating it myself. And it's not incorrect to do that, but why not use the system calls made available for you to do the work for you, right? There's less opportunity for making a mistake. So I'm going to call size of, and size of takes a single parameter. And in this case, I could create an integer variable and return from size of assigned to an integer variable and use that as the parameter. But the style I like to do, and you see it many times in C code examples, is to call size of directly inside the malloc. It's not incorrect to have an additional step. So size of what? Size of struct rec struct, right? Because that struct rec struct is a type. So what this says is call malloc, and malloc is going to get as a parameter. There's a bug flying around. Malloc is going to get a parameter, and that parameter is the return value from size of, which is the count of the number of bytes that type rec struct occupies. Now, of course, if I wanted to allocate space for floating point number, I would just say size of float or size of int, right? So you give it a type, not a name, but a type. Because remember, when I say struct rec struct, that is a type, right? Just like how you'd say integer or Boolean. Okay, so let me put back the struct rec struct back there inside of size of. Now, this is the size of a single one, but I want a list of 3 of them. So I'm just going to take this return value from size of, and I'm going to multiply it by num rex, right? And num rex in this particular instance is 3. So it says allocate some number of bytes. How many bytes? Size of rec struct. How many? Times 3. Okay? And so all of that calculation is done for me. Okay. Any questions about this? Make sense? Yeah. All right. So now that I've allocated my memory, when you allocate memory, it doesn't know what that memory should contain. You just tell malloc, allocate this many bytes. But now you have to tell your program, this is how you're going to interpret those bytes. And if you look at the help documentation for malloc, you'll notice that malloc returns something called a void star. Just now. All right. Man, malloc. So if you look at malloc, at the function signature for malloc, malloc takes a size, right? That's the single parameter, just as we had discussed, and it returns a pointer, to void star. Void is this in C, the way you represent something called nothing, right? So it returns a pointer to a nothing type. Void is the type you use when you don't have integer float or any user-defined type. It's this non-type type, which doesn't make sense, but you need to have concrete values when you're going to do a compilation. And so what void says, it's not one of the built-in types that come with the language, like float, integer, and it's not a user-defined type. It's this nothing type, okay? And so when we do this malloc, of course, it's going to return a pointer to void. And now we need to tell our program that what started out as a nothing pointer, I want you to make it look like a pointer to these rec structs, because that's what the records pointer is expecting to have. So I'm going to do what's called a casting operation, struct rec struct star, right? And so what that says is take this void star and make it look like a pointer to these rec struct types, which just happens to be a user-defined type laid out as described above in the structure definition. Okay. Any questions about this? Make sense? And so what this casting will do for you is it'll merrily try to make memory look like whatever you want it to. Now, C has the philosophy that if you want to do something, regardless of how normal or abnormal that might be, you must have a good reason to do that, so it lets you. So, you know that famous saying, with great power comes great responsibility, and C definitely follows that. There are many ways you can damage the operations of a system with the C programming language. And so if you had an array of characters, you could take that array pointer and cast it to an integer, and it will merrily take those characters, every 4 characters, and make it look like integers, right? It allows you to do whatever you want. And in this particular case, we're saying those size of struct rec struct times 3 many bytes that we allocate, I want it to look like a pointer to struct rec structs, right? So that's what that so-called casting operation does. I have the open and close paren. I have the type, which is struct rec struct and star. If I wanted to make it look like an integer, I would just say take those bytes and make it look like a pointer to integer, okay? And C lets you do that. Now, of course, if you have underlying memory that's filled with values and you do this casting operation to something that it is really not, it'll still make it look like that, and whatever memory happens to be there, it'll take those bytes, chop them up into the right set of groupings, and make it look like an integer or a Boolean or what have you. So you really want to be careful when you do this casting. You want to be careful that A, you have enough bytes that you allocate to represent the data structure that you're trying to represent or store in memory, and also make sure that you match up the types, because C will let you do this mismatching. Okay, all right. Any questions about this? Make sense? Okay. So in this case, I have enough memory stored in which to store 3 of these rec struct data structures, which are user-defined types. So the next thing I'm going to do, when you allocate memory, right? Memory, starting out when you boot your system, it does this thing called the marching ones test. And the reason for the marching ones test by the firmware is that it wants to make sure all of the parts of the system are working, including memory. And so what does it do? It writes a repeating pattern of 10, 10, 10. It's called the marching ones test in all parts of RAM. And then it reads it back to make sure that all parts of RAM are working, right? So if you first boot your system and that part of RAM hasn't been used by anybody or allocated, you go ahead and you allocate some block of memory, and we've done so to store 3 many of these rec struct data structures. Now, that memory is still going to have those values that were there when we booted the system, 10, 10, 10. So whatever that would be, if we interpreted the first 1024 bytes as first name, the next 1024 bytes as last name, and the next 64 bits or 8 bytes as a float, well, you're going to start out with a floating point value in each one of those copies of memory for each of these 3 rec structs. And so it's really important when you allocate memory to initialize it to a default value. And so what we're going to do is set all of that memory we just allocated. We're going to set it all to 0 and use memset to do that. So unlike languages like Java and other more modern languages, Python, when you initialize a variable, it's doing some work for you underneath the covers. And what it's doing in Java in particular, the Java class loader initializes all instance variables to some null type value. So all numbers are initialized to 0, all references are initialized to null, right? And that's a convenience, but C doesn't do that. So I'm gonna set these, mem set the records, starting at the records location. I'm gonna set that to 0, and the number of bytes I'm gonna store is gonna be size of struct rec struct times num records. Okay? So again, I'm going to use that size of routine to count the number of bytes. When you issue the memset function call, right, use that system call, you have to give it the starting location where you want to set to 0 in this case, what you want to set it to. I chose 0, you could choose whatever you want. You could set something to a character if you want to, or a blank space or what have you. So starting at address location, the records, it's a pointer, I'm gonna set size of struct rec struct times 3, enough bytes to represent 3 copies of that user-defined type. I'm gonna set them to 0, which is what my initial value is, 0, in that call to memset. Any questions? Make sense? Yes?
What was the third parameter for memset?
The number of bytes. The third parameter to memset is a number of bytes to set to 0. And so memset, let's take a look again at the manual pages, memset. And so memset has 3 parameters, void star s, so it can be a pointer to anything, followed by int c, a count, and size t, n. And so if we come down here, let's see if it has the parameters. Okay, the memset function fills the first n bytes, right? So that's the third parameter, n bytes of memory area pointed to by s with the constant byte c. And so the first parameter is the starting location. The second parameter is what you want to initialize it to. And the third is how many bytes you want to initialize. Okay? All right. Any other questions? Make sense? All right. So let's exit the manual pages. All right. So we have our initialization. So now that we have the records, you can imagine this as an array. We have enough space to store 3 of these rec_struct data structures. And what I'm going to do is I'm going to loop through them, and I'm going to ask the user of the program in the command line to type in information, and then I'm going to then print out what was stored, and I'm going to free that memory. So let's define a loop for int I gets 0, I less than num rex I plus plus, and I like to begin and end the block before I fill in the details, right? And that should kind of be a habit. It helps you avoid those nasty error messages. If you don't close a block in C, the errors start to propagate. You'll get an error message somewhere completely different due to not closing a block. And so it's good practice when you're programming to close the block immediately. It helps you avoid those propagating errors. So I'm going to take the records, and I'm going to do a printf, enter first name, right? So print out a little message here, and then scanf a string, %s. Now when I scanf this string, what scanf is expecting is going to be a pointer to a character or a character array. And here inside of my rec_struct, right, I have as my first piece of information in one of these rec_structs, I have a character array. And how I would access this character array is just using the name of this character array that acts like a pointer, right? But I have a little bit of an issue here. I can't just access the rec_struct directly. I have to access that list of rec_structs first. And so I need to dereference that pointer, right? And in order to dereference it, I need access to the pointer variable before I can access one of those elements of my first instance of a rec_struct, okay? So I'm gonna set another variable called record, and it's gonna be a pointer. And the reason for this other variable is I need something that can look at the first one, the rec_struct, look at the second rec_struct, look at the third one. Now you might wonder, why am I creating another pointer to do this instead of using the records? I don't want to modify the records, because if I change that, I'm going to lose my location of where all these 3 records exist in memory. So I'm going to create, sometimes it's called a cursor, right? Something that moves to mark where you are. So I'm going to create a cursor, and I'm going to call it record. So struct rec_struct star a record equals null. And a record is just going to be another pointer variable that I'm going to vary as I'm going to the first element of the list, the second, the third, and so forth. And so I'm going to start out, I'm going to initialize a record to be the same as the first record, which you can access through the records. Okay? That make sense? Questions? And so I have 2 pointers, and the records tells me the starting location of that block of memory where I have 3 of these rec_struct data structures. A record is also going to point to that starting location because I copied the value of the record's pointer and I assign that to a record. And the reason why I created a record is because I'm going to change that as I go to the second one and the third one. I can't change the records because I'm destroying my value that stores the beginning of the list. I want to keep the beginning of the list separate from that variable I used to iterate through the list. So when I do a scanf, I'm going to dereference a record. So I say a record. And how you dereference pointers to structure, use what's called arrow notation. Dereference that pointer, and when I use that arrow notation, right arrow, it dereferences that data structure, that instance of recstruct that happens to be at the starting location on the first iteration of the loop. So now I say first name. Okay, and so first name, when I do that arrow notation, I gain access to that particular part of memory for the first one, and first name is that element of the structure that I'm going to access. And it just happens to be that that first name element of the rec struct is a character array. It's the name of the variable for a character array, and it's exactly a pointer. Character array and pointer are the same thing. A character array is like saying a pointer to char. Okay, so I print out enter first name, and then I get input from the command line for filling in what was typed on the command line, and I store it in first name for whatever rec struct instance happens to be accessed by a record. Okay? Questions?
So by dereference, you mean your A record is no longer pointing to the record, but being pointed to record?
Great question. So I wish I had something to draw with. Let me get a marker, and I will do it on the board here. It's going to be hard for people in back to see. I wish I had a little board that was higher. So here we have system RAM. Well, that marker's not working.
There's a marker right there. It was on this.
Oh, okay. I have a little stash, thank you. I'll just leave this one up here. Every year I make a Staples run and a whole bunch of markers. All right, there we go. So there's RAM. So I execute my malloc, right? And when I do the malloc, I have enough storage because it's a contiguous block of bytes, and that storage is enough to store 3 of these rec structs, right? So that block starts somewhere and ends somewhere, and this is referenced by the records. Okay? So this is the state of my system when I do that malloc, right? Okay. Let me, in green, let me sort of draw boundaries for the 3 instances of my rec struct. Okay, so that's what happens when I do the malloc and I do that casting operation. So now the next thing I do before I start the loop, I say a record is equal to the records. So if I say a record is equal to the records, I have a second pointer, it's called a record. And I'll just take a photograph of this and splice it in on the video. So I, before the loop, initialize a record to the records. So now, when I do the scanf, if I say a record, arrow notation, I'm now saying access that memory location that stores the first instance of one of these struct rec structs. So what I'm doing is I'm saying, okay, well, now go in here, now make that dotted line, and now access the first one. And the reason why I'm accessing the first one is because at that moment, a record points to the starting location, and the starting location is where the first one is located. okay? And so inside of this rec struct, let me just kind of blow this up, right? I have a record, right? And it points to a memory location. That memory location is the starting location of one of these rec structs. So if I have one of these rec structs, it's much bigger now. It has first name. It has 1024 characters. So this is, that's character 0. This is character 1023. So it's 1024 characters. And that 1024 characters is accessed by something called first name. It has another 1024 characters. That's character 0, character 1023. That's accessed by last name. And then lastly, and this is not drawn to scale, it has 64 bits or 8 bytes, byte 0, byte 7, and that's called balance. Okay? So when I use this arrow notation, it's now allowing me to access this particular instance of rec struct. And now when I use the variable first name, it's giving me the address of this array, which is referenced by the name first name. Okay? And so the arrow says, access that particular one, and then the variable says, get me this piece of information from inside of that first one. Does that make sense? Any other questions? Okay. Now, equally, I could have said star a record, right? Because I can access pointers, the location of memory referenced by pointer with star. But the problem with that is if I say star a record, that gives me the entire contents. I don't want the entire contents. I want part of the entire contents. And I'm just getting, using the name, first name, that particular part of the entire contents, which corresponds to the first 10, 20, 24 bytes, which are characters. Okay? Make sense? Okay. So I'll leave that up there, take a picture, and find a way to splice it in on the video. Oh, what just happened? Oh, it looks like my screen lock. All right. OSC. All right. So I print out a message to the command line, and then I get input from the command line from the user and store what was typed, a string, inside of that first record. So I'm going to do the same thing with the last name. Printf, enter last name, and scanf, a string, %s, a record, last name. Okay. And then lastly, I'm going to do the same thing, similar thing, with the floating point balance. So printf, enter money, okay, scanf, and you notice here scanf, it's a %f because it's now going to interpret what is typed as a floating point number, right? And I'm going to say record, arrow notation, get me that part of it referenced by balance. Now, the difference here now, you'll notice that balance is just a straight variable, right? It is not a character array, and balance is a basic type, and basic types, if I did this, it wouldn't work. Scanf needs an address of the thing it's going to fill in. It just happens that when I say char array, right, the name of the character array is a pointer to a character, so it's already a pointer. So now I need, for this third scanf, because it's a floating point value, there's no pointer there. I need to get the address of whatever this variable was. So I'm going to use this address of operator. I'm going to first encapsulate this in parentheses. And so the arrow notation, a record, arrow balance, that gets me that variable balance. But I don't want the variable, I want the address of that variable. So I put ampersand in front of it. So a record, arrow balance says, access the first memory location where the record is stored, get me that variable, that region of storage that happens to be 8 bytes long. It's a float, if it's float 64, which typically is IEEE 64-bit floating point representation. Get that floating point variable and return back the address is what that ampersand means. Now, of course, I want the access of that balance variable or area of rec struct to happen first before I get the address of it. So I put the parentheses around a record arrow balance before I do ampersand, which is address of. Okay? Any questions about this? Okay. So now that I do that, I'm all set. Let's go ahead and print out all of these values. So I'm going to loop again through it, resetting. I've forgotten something. So now, and this is the beauty of what pointers can do as it pertains to structures. Once I'm at the first instance of a rec struct, the next iteration of the loop, I want to go to the next instance of a rec struct. Now, this type has a certain number of bytes. If I have a pointer to that type, if I say pointer plus plus, increment the pointer, I'm now incrementing enough bytes to point to the memory location of the next one. So if I say a record plus plus, increment it, what that's doing is taking a record, the old location is the first one, and the new location is that start of memory where the second instance of rec struct is in RAM. Okay? All right. So now at the bottom of this loop, as a consequence, once I'm done with inputting information for the first record, I'm going to say a record plus plus, right? Go ahead and advance the cursor to that to the next memory location, not next as in, one memory location away, but the memory location for the next instance of a rec struct, okay? All right, so we do that, and there's our loop. So let's go ahead and let's print out all of these contents. For int j gets 0, j less than num rex j plus plus, open and close the block. Oops. So now we're going to loop through, and we're going to, for each record, we're going to print out the name, first name, last name, and the balance. So printf, and I can do it in one fell swoop. Percent s, that's the first name. Percent s, that's the second name. Percent f for float, that's the balance. Has percent f. So it's going to say first name, last name, has, and it'll say a dollar amount, right? Okay, \n, new line. So substituting for the first string, I'm going to use the first name part of the rec struct. But I'm going to start out again, record. I'm going to initialize that to be the starting place of all my records, because because when I do this increment in the loop above, the for I loop, that pointer, a record, is going to now point to that last item in the list. I want to reset it back to the first item. So I'm going to print out a record, arrow notation, first name. I'm going to also print out for the second character string, record, last name, and then lastly, the %f, I'm going to print out the balance, record, arrow notation, balance. Now you notice here, when I printed out the balance, I didn't say address of, because I'm not trying to set the value, I'm trying to get the value so I can print it out. So the reason why scanf needs addresses is because if you're going to fill in information, you need to know the memory location where you should store that information. And so that last parameter on scanf should always be an address, okay? Now, if you don't specify an address, it'll treat whatever number you give it as if it's an address. And if you gave it address 0, it would try to input something in the 0 location of memory, which is owned by the kernel. You'll get a trap, and your program will be kicked off the processor. You should try it. It does work. All right. So we print all this out, and then we return 0, and we're done. So let's test this out. Any questions first? No questions? All right. So, yes. Oh, yes. Thank you. See if everyone's paying attention now. I actually forgot. Thank you. Yes, we need to free the memory. I was being a bad C programmer. All right. All right. So we have to free the records. Absolutely. Forgot to free it. Now, the thing that's particularly damning, right, is let's say, this is a fairly simple program. It's just a main routine. Let's say if you had a big program with a lot of functions and, you call some functions and each function is allocating memory and the functions don't free back the memory, you have what's called a memory leak. It's just going to keep consuming memory, consuming. And there are some professional pieces of software, which I won't mention, that you ever notice, you keep them running and all of a sudden your system gets really, really slow. And it's not until you kill off that program that things kind of perk up again. And that's because there's a memory leak somewhere. And you can actually try that. Run certain pieces of software, bring up your system performance meter, look at how much available RAM you have left. And you notice for some pieces of software, if you run it for a couple hours, you notice the amount of available memory keeps getting sucked up by this program, and that's because they're not matching their mallocs with their frees. And so yes, absolutely, you're supposed to free all the memory that you allocate. So I'll add that free there. Okay, any other questions? No? All right, so let's write that and quit, and let's run the make file. There are no errors. Well, I did practice ahead of time. So let's run test structure. So main started, enter the first name. Let's say Mary. Okay, Smith. Mary has, $375.89. Okay, first name, let's say Bob Jones. Okay, and Bob Jones has, $289.23. And say Gary Holness, and because they don't pay professors, $7.54. Okay, all right, so let's try that. Oops, something happened. Mary Smith. So what do you think happened? There's a bug. I know what the bug is. What do you think happened? It's not changing the name, right? So something has to have happened with the pointer that I'm using to do the printout, right? And that just tells me immediately I'm probably not incrementing the pointer a record in that second loop. So in that second loop J, it's exactly the case. I have a record, but I don't increment it, right? So a record plus. Because I initialize a record to point to the first one, I fill them all in the first loop, and you notice at the bottom of the for I loop, I say a record plus. Go to the next block in memory, go to the next block in memory. But I don't do that when I'm printing out, so you saw Mary Smith happen 3 times because it was just the first one. So let me make, and let me rerun it. So Mary Smith has, I think it was $375.69 or something like that. Bob Jones has $289.34, and let's say Gary Holness has 7 and change, $7.24. Okay, so you notice here, after I entered these in, I print them out, and you'll see all of that information has been stored in RAM, and I can print it back out. Okay. I could equally as well, instead of typing it at the command line, I could have read it from the file system, right, from a data file or from a database. And then instead of just printing it out to the screen, I could have stored it to a database, for example. Okay? All right. Any questions about this?
Well, that's the favorite point going from 69 to 69 is yours.
Oh, yeah. That's because the precision, I didn't give it any precision. I should have said floating point, where the decimal point only had 2 digits. And so because it's a discrete representation of a continuous construct, if you carry out too many decimal places, sometimes it's off. This is the plain vanilla C runtime library, but there are other libraries that are more precise when it pertains to floating point numbers. And so that's just an artifact of the fact that I didn't limit my decimal place to 2 places, because it is an approximation. You can never get a true real number from a computer representation. So that's an artifact. I should just limit the representation. Good question. All right. Any other questions? Okay. With that, I mean, I can certainly post this, but I'd rather you try it yourself and tinker with it and get comfortable with how it works. And the reason for demonstrating this is that when you look at various operating system data structures like a process control block is nothing more than a struct, right? It's called a task struct. So somewhere in the Linux definition, there's something called struct, task struct, and it has all these different variables in this user-defined type that store information about the process context, right? And so it's really important to get comfortable with being able to work with pointers to structures and what structures are. And it's nothing more than a user-defined type. You're extending the types in the operating system with custom layout data types. Okay? No questions? Any questions? No? All right. So let me exit this, and I'll minimize that. And let's go back and spend the next about 10 minutes or so continuing on with material on processes. Okay. Oops. Did that work? No. Decided not to work for me. All right, so I'm going to have to do that old school, sitting at the terminal. My clicker doesn't want to work. No. Remote's in. All right, let's just do it this way. So last time when we left off, we talked about process scheduling, and the process scheduler is that part of the operating system that selects among available processes, and these will be processes on the ready queue, and these processes that are available for execution. Now, of course, when you make that selection, you being the operating system, that selection can be fair, or it can be unfair with a prioritization scheme. And so the process scheduler selects among all the available processes that are going to be, from among them, that process is selected, that is going to be the next one to get some fractional use of the CPU. And so there are lots and lots of scheduling queues. Processes will wait in line for various purposes. The same way you'd wait in line at a bank or wait in line at the registrar, DSU, you are waiting in line, you being a process, gaining access to all sorts of parts of the machine. And so there's something called the job queue, and the job queue contains a set of all the processes available in the system. Now, there are other queues that contain subsets of all the available processes. One of them is the so-called ready queue, and these are all the processes that are physically in main memory. And as due to the fact that they're in main memory, they're available to be put on the processor right now. Now, of course, not all processes might be in main memory. Some of them are going to be waiting for I/O. And each device has associated with it a so-called device queue, and that device queue contains a list of process control blocks associated with processes that are waiting for that particular I/O device. So for the network card, the disk I/O controller, the DMA controller, and all of those pieces of your von Neumann architecture, you're going to have queues associated with processes that are waiting for that device. Okay, and so certainly these processes, when you're done with the device as a process, you're going to migrate from one queue to the next. It's kind of like, on welcome weekend, first you're going to wait in line to get your student ID, and then you're going to wait in line to get your dormitory assignment, and then you're going to wait in line maybe to get some food for lunch or what have you. And so in similar fashion, these processes will migrate from one queue to the next. So if you call a system call maybe to read a file or to read from the network card, you're going to wait in the device queue for that particular I/O device. Then once you're no longer waiting for I/O, you have that information, you migrate back to the ready queue, and then you're scheduled from the ready queue for execution for some period of time on the processor. So certainly over time, processes will migrate among these various queues. So let's continue on. And so this is a depiction of these queues. So a queue is a basic data structure, and a queue has certain semantics. You have a head and a tail, and the semantics of the queue is that you pick from the head and you add things to the tail. So it's first in, first out, or FIFO for the operation of a queue, which in contrast to a stack is last in, first out. LIFO, right? So stacks and queues, they look the same, they're linear lists, but they behave differently. And so up at the top, we have the ready queue. And so we have our PCBs associated with the ready queue. We have a pointer to tail that identifies the end where new incoming ready processes are placed. And then you have the head, which is where the first one is. Now, depending on your so-called scheduling discipline, meaning the criteria you employ as to which waiting process, which ready process is going to be selected, it's not always necessarily the first one, the one at the head of the queue. If you have prioritization, you have multiple queues, and one queue would be the high priority queue, and you're going to select from that one first before you select from the regular queue. So nonetheless, we have at the top our ready queue, and we have a few device queues that are listed there. So there's magnetic tape device queues. There's a disk device queue for disk device unit 0. There's one for the terminal for processes that are waiting for input. And so, like you saw with the C program that I wrote, when I was sitting there not typing anything, the process was waiting for me to give it user input. And the moment I typed and hit enter, all of a sudden that process continued with the next statement in the code. And so this is a big queuing system, and queuing systems is how you organize a lot of complex interactions when you have multiple entities that are contending for a limited set of resources. And in fact, when you analyze things like restaurants and bathroom usage and things like stadiums, they actually model this using queuing systems. Okay. Any questions about this? Okay. So this is a representation of the interaction or migration of processes between different queues. And so in these queuing diagrams, what you're after is looking for pinch points, right? Are there places where you have a lot of entities that are waiting in line in the respective queues? And in fact, one of the big deals is bathroom design, right? When you design bathrooms, typically the practice is to have an equal number of stalls for the men's room or for the women's room. But what queuing theory talks about is something called service rate. And so you notice in stadiums and rest stops and things like that, you see a line in front of the women's bathroom, and you won't see as long of a line in front of the men's bathroom. And so when you're designing a system, one of the things you have to take into consideration is so-called service rate, how long it takes each item to execute and then leave the queue, right? And so when they do bathroom design, they don't take that into consideration, unless it was designed by a female who takes that into consideration. And typically how that results is you have more stalls in the women's bathroom and fewer stalls in the men's bathroom, because you only have so much real estate for doing bathrooms. So if you ever go to a stadium or you go to a rest stop, certainly it's kind of a challenge to go visit both gender bathrooms, but if you find that there are more stalls in the women's room bathroom than the men's, that means the architect was female, right? Because unfortunately, some people don't think about those issues. All right, so nonetheless, we have our queuing diagram, and here we have our ready queue, and you're scheduled by the CPU for execution, and two things can happen when you're picked off of the ready queue. You execute on the CPU and you exit the system. That's that outbound arrow that goes off into space. Or you execute a system call, and that system call forces you to wait for some I/O operation. And so you initiate an I/O request, and now you're waiting in the I/O queue, the second pathway coming out of the CPU. Another thing that can happen is you're executing on the processor. It gives you some standard unit of time, delta t, in which to execute, and your time has expired. And so the operating system throws a software interrupt, a trap, and now that trap indicates to that process that it's time for you to go. Its process control block, its context is stored. So all that information is scraped off the CPU and populated in the PCB structure, and then that process is kicked off, right? So if your time slice expires, you're kicked off the processor, but you're still in a ready to run state, so you join the back of the ready queue, right? So that's that second edge. You can also, as a process, fork a child process. So a process can start another process. And in the beginning, when you start another process, that child process, or the thing that you start, is an exact copy of that program that called the fork command. And then typically what happens is you execute a different set of code within that child process, and it's called execing. So typically, when you start a child process, it's the fork that splits you into two copies, like cloning, if you will, and then the exec says, take this copy and load a different program into that process. Okay, and so when you fork a child, that is a system call, and so you're kicked off the processor as a result. The child program executes, and you're taken off the processor, and then both the child process and the parent process that forked and exec are put onto the ready queue. Okay, and lastly, when you're waiting for an interrupt, maybe it's some interrupt for a system, maybe it's a timer, a general interrupt, is something that causes you to get kicked off the processor, and you're waiting for that interrupt to occur, right? And so you kicked off the processor, you put in another queue where you're waiting for the interrupt. Once the interrupt fires, your execution resumes, and now you're back in the ready queue. So this describes at a high level the flows between queues and processes, or more correctly, process control blocks are being taken from one queue and put in another queue, and they switch around all the time based on the events that happen on the system. Okay, so let me do a time check, 10:37. So there are lots of schedulers in place, and again, the scheduler is the quantity that makes a decision for when to execute a particular process. Now, there's something called a short-term scheduler. And the short-term scheduler is the one that decides which process should be executed on the CPU. And if you think about what's happening, because each process is given some standard unit delta t of time to execute on the CPU, this short-term scheduler is effectively sharing out fractional usage of the CPU. So once your quantum or your unit of time expires, you have to get to the back of the line, right? You've used up that particular fraction of the processor. There's something called the long-term scheduler, and the long-term scheduler decides which process should be brought into the ready queue. And the long-term scheduler's job is to decide how many concurrent actions should be happening on the system, right? Because you want to limit, in a sense, the number of concurrent actions because you have finite resources. And after a certain point, you can exhaust all your resources, and you don't want that to happen because your system won't function properly. And that's especially important, and people watch for this as it pertains to server applications. If you think about certain modern internet concerns like Amazon or Netflix, their entire livelihood is based on the ability for their server processes to deliver content, right? And without those Amazon servers working, they don't make money. Without the video streaming, Netflix doesn't make money. And so they really want to make sure that they're not exhausting the upper limits or going beyond the upper limits of the resources that each machine has. And so there are lots and lots of techniques that people have for it. And sometimes you find when you try to access a website, rather than have it crash on you, they don't allow you onto the system, right? It might say, oh, the server's busy, please come back, right? And that's a much more desirable action, even though it's not pleasant. If you get that, it's much more desirable than to have it fail while you're trying to use it, right? So by limiting the number of requests for resources, you can guarantee that everyone that can get resources can get a good service when they're interacting with the machine. Okay. Any questions about this? All right, so let's stop here, and we'll continue on with something called the medium-term scheduler, and go forward on Tuesday. I'll see you all on Tuesday.